I guess I'm just gonna start because we might as well. Does anyone use a 3D scanner in the audience? I got one person. I got you two don't count. Anyone else? All right. So that's what we're kind of going to talk about today is using digital workflow, digital data to do your things. Mostly like a lot of the OEMs here and the big manufacturers do a lot of that data. And what they do is you need a way to create CAD models, to do reverse engineering, to do first article inspections, and this is kind of what I want to talk about. It's just not a lot of people. There's not a lot of knowledge about it, like outside of major OEMs. So we just want to talk about that a little bit and just kind of give like an overview of how you can get your products to market quicker, get your design done faster, get the manufacturing faster, and then be able to check stuff when it comes in a more efficient manner. And then anybody here build stuff, like send stuff out to manufacturers, do like design work? Sweet. So first things first, just a little thing, kind of like digital manufacturing thread. Obviously we put a 3D scanner in the beginning because that's what we do. But this is, can include any measurement method. So like right now you might go out with like a ruler, you do a bunch of hand measurements, you might program some stuff for CMM to probe out parts that you need to reverse engineer. And we can use essentially all of that data as part of this. We're going to take that in, we're going to put it into our CAD environments, our design environments, and then we're going to push that to however we want to go to manufacturing. And once we go to manufacturing, whether we're doing it in-house or outsourcing it, we're going to bring back parts in, and then of course we have to check everything because probing stuff out in the CNC machine right after you cut it isn't the most accurate way to check things, because if the CNC machine is off, the probing is also going to be off. So it's just kind of how these things work. You always need sort of like an external inspection thing going on. And then that's part of our feedback loop to go back for like design revision and or redoing our CAM or our manufacturing programs to adjust for those inaccuracies and things like that. So we're going to be talking about mostly like the some of the data acquisition, but then also like once you acquire data, like what do you do with it? So and a little bit about just kind of like when we talk about reverse engineering, it can really be like anything. You pick up measurements, anything on a vehicle. You can see where something goes, and it could be as simple as like laying out a paper template, or just drawing something on a piece of paper and putting dimensions on it, or it can go through something where you are pushing things out in a CMM, programming parts, and acquiring data, and then using that data in a way to create. And when we say CAD model, we have to think about like what do we mean for CAD as a CAD model. So different measurement techniques. So we talk about measurements, some of the ways that we look at things and how we visualize measurements. When you have a couple hand measurements, you're only taking very tiny snapshots, like 1 or 2 or 3 or 5 things on a part, and that's kind of defining that part for you or that assembly for you. Whereas when we go into digital measurement methods like probing on a CMM or on your CNC machine, we're requiring a lot more data on the part. We're probably maybe taking like 50 points or 60 points over an object. And again, that's giving us sort of like a limited view of what is there on the part. It gives us enough information to probably pull out like, is that bolt circle right? Like, are these cylinders in the right spot? Are these holes lined up the way they're supposed to? These things that are supposed to be perpendicular or parallel to each other, like are they accurate? Did we face something wrong? Is the height wrong on the shelf? Stuff like that. When we go into 3D scanning, you can just think of that as taking what you would do in a CMM, and instead of doing maybe having like 50 measurement points defining some features, now we have millions of measurement points all over the object. So creating like what we call a giant point cloud or a bunch of mesh data. And then when people say CAD, like these are some of the other things that we like to talk about, is like, what do we do when we're talking about CAD? It's like, so CAD can pretty much be anything computer aided. So like those 2D AutoCAD drawings from back in the day, that's still CAD. So, and it's like mesh models, still CAD, it's just a different form. Create NURB freeform surfaces on things like you would see in like a lot of product design, everything else, that's still CAD, even though it may not be something you can machine from easily. So we need to think about like what our definition is of CAD and how we want to bring that into our current workflow that we need to get parts out the door. So, and then different manufacturing technologies like different types of CAD. It's just kind of how it is. So, if I'm doing laser cutting for sheet metal parts and things like that, that 2D line drawings are all the CAD that I need. If I'm going to be doing CNC bending to get that sheet metal into 3D, maybe I should have started with some 3D CAD instead and then flattened it out to do my sheet metal components. But there's all these different methods to do it. So acquiring lots of data kind of on an end-use part or pre-design, helps me just inform my design process, helps me set requirements on what my design needs to be, and then what type of CAD that I need. So, and then, if we are going to scan stuff, we're pulling things in, regardless of our measurement methods. Just like if we had a CMM, that might just be our all we have for creating our features. We would take those measurements, and then we could manually translate that stuff into our CAD programs, where we're going to do our modeling based on that measurement data. When we get into things like 3D scanning, we have millions of measurement points. We generally have big point clouds or mesh models. And it's like, well, how do we use that data in our CAD packages? Because at that point, I don't really have something that's just a couple tangible features to make a model from. Now I have something that has a fully encompassed amount of data over a part, over every single surface and everything else, and like what's important. And then what do I need to do to get that into my CAD environment so I can have a workable model for whatever type of CAD that I'm using. So, and then the answer to that is always a bridging software. So, I'm with Geomagic, the full disclosure. We're like probably we're the oldest company in the business for using scan data. We're talking like 20 years now, back when people first had digital cameras, like in the 90s, and we're taking pictures and turning that into 3D point cloud data based on ranging. And there was one or two other people that were doing research kind of at the same time as our company was, of like how we could actually use that data besides just like as a graphical representation. So, and we've been creating bridging software ever since with a bunch of our Geomagic programs for creating, just doing mesh modeling, but then also doing surface modeling, and then doing parametric modeling like you would in SolidWorks and Inventor and in Fusion and stuff like that. And then also like how we focus on using that same millions of points of measurement data in a quality control aspect. So, and a little bit about more, so again, pretty much everything's CAD, so it's really just depends on what you want to do with it. But when I'm talking about CAD, I'm mostly talking sort of like parametric data, like you would have in a machine part that you would stick to a CAM system that you'd be able to like cut parts from and things like that. So and there's lots of different deliverables again when we talk about CAD models. So that point cloud generally, not a lot of people would consider that a deliverable. A mesh model people might consider deliverable though, especially with additive manufacturing. I can go and get those mesh models and those clean scans, and I can send them directly to a 3D printer to print another part out. So that might be my end goal. Like maybe something broke, I snapped a clip on something and I need to redo something. I could scan that part in, clean up my mesh model, and then I could just dump it right to my 3D printer, print it back out, put it right back into service. So, a lot of repair stuff that way. Back in the day, so I have quick services on there. If we were talking 15 years ago, a lot of times when people wanted to CAD from scan data, they were like, well, how fast can I get the NURB surfaces? And I don't know if CAD guys will understand what NURB surfaces are, but it's really just a bunch of patches on an object defining the boundaries of that object. So there's no cylinders, there's no planes, there's none of the things that you would think of in parametric CAD if you were modeling something as an engineer. But they're very useful parts nonetheless. And if you're doing tooling that has lots of sculpty surfaces and things like that, they tend to be okay. So that's another deliverable. The other one is using a mixture of the two, where you'd have a lot of those kind of patch surfaces on a part, and then also adding regular parametric CAD to that, because you're going to have interfacing things where you need parallel planes and perpendicular planes and specified cylinder diameters and locations and everything else like that. So we might actually mix those together, and then we would use those in what we call hybrid modeling. And hybrid modeling is becoming a big player now, especially in the automotive industry. They're doing a lot of topology optimization on parts, making parts that are generally only castable, that you couldn't really machine without a 6-axis or something like that, or some other fancy types of equipment. But a lot of these are really easy to do with additive manufacturing and metals and plastics and things like that. So we could really do a ton of weight savings on parts. And if you look at a lot of the concept, automotive shows and things like that, concept vehicles touring out, you're seeing a lot of additive manufacturing components. Most of those are what we considered hybrid models as we're creating them. So, And then we also have to decide what we want to do when we're talking about reverse engineering, like what do we need for our part. So we can do stuff as built. We could just say like, hey, this thing fit together. I'm going to recreate this. I'm going to make it exactly the same as it was. And we're just going to put it in. It worked the first time, and it's going to work again. So a lot of times in older equipment, older vehicles especially, as you guys all know in the automotive field, even OEM tolerances on new cars leave a little bit something to be desired. So if I get five GM products and they all use the same part or whatever else, and they're all set up, I might measure all 5 of them and be like, wow, these things are kind of all over the place. Like I would expect them to be accurate within a thousandth of an inch. It's like they're kind of flayed all over. And if you have 5 different assemblies, like you got to think about like tolerance doctors. So then you're like, well, maybe I don't want to make the part exactly as it is. I probably want to look back and see, average these measurements and talk about like what the original engineer design intent was of the modeling. So this is where the parametric modeling really comes in, and being able to use Scan to do that is we can go through and create a model that has the original engineering intent and then put our tolerancing on top of that, which is what we find that they're using on their part. So I can create something that's a direct replica drop-in, and it's going to fit their spectrum of products the exact same way. So, and then, again, get you a couple product examples of things that are people doing, and it's like, well, why are, we think about why we're doing reverse engineering. Like a lot of times, especially with custom vehicles, you're going to make that first part, and you're probably going to do a lot of hand work in that first part. You're going to go through, and you're going to grind stuff, you're going to bend it, you're going to force it into shape. Maybe you're doing like some foam buck models and things like that if you're doing body work or whatever else, and like hand sanding it all into play. I'm just guitar as an example because it's just a really easy one. What you think of is a lot of the guitar manufacturers, like they're going to go in, and this guy's going to take a piece of wood, he's going to turn it into the guitar body he wants, it's going to fit really nice, it's going to get everything where he wants it, for any person playing. And it's like, well, what's our next step? Is, well, we want to produce this. I need to make, I want to sell 1,000 of these. I don't want to make one at a time. It's not very cost effective. I want to get them in market. So we need to think about how we want to use our CAD to like recreate that model so we can have it fully digitized, and I can send it to a production shop, or I can send it to my CNC routers and everything else like that. So, we might also be doing like CAD and tooling correction on stuff. Like if you have, if you're doing stamping or something like that in sheet metal or whatever else, stuff wears over time. So we might need to like recreate some parts to go through and update what our original tooling was, or maybe you bought tooling from an old manufacturer that used to make something, and you're trying to make new parts out of it, and you're like, hey, this stuff's really beat up. I really need to machine some new tooling out, new dies to put in things, redo a fixture that's just like seen its years worth of work put on it. Stuff's got banged around a lot. So we use the scan data and all those measurement points to really easily update a CAD model. So, or reverse engineer what the CAD model would be for that fixture. So, and then, when I was talking about parts that have varying tolerances on them coming from OEMs and things like that, like we do a lot of, use scan data as one of the fastest ways to get that average data. Because the acquisition is really quick, and I don't have to put it in a CMM and probe it out and write a program to do that and find all the things, and then I just have a bunch of tabular data. And you think about if I went and created 3D scans of all those parts, I can easily let the software average all of that data and give me my best quote-unquote part of like what that best average is. And then I can use that as my design intent for recreating tooling and things like that. And this is done a lot in like the gearing and power gen industries, but it's also done a lot with like automotive components and things like that. Like if I'm looking at like 1970 Chevy water pumps, they're like all over the place with their design. The castings were all over. They might have had 7 different production facilities making that same water pump, and they all had different intricacies to them. So if I'm going to go and make it for my recreation part, maybe I want to grab a couple from each one of those suppliers, scan them, average them together, create like a part that I know with 99% certainty is going to fit like every vehicle that I come up against. So, and then again, with topology optimization, a lot of times we're getting a lot of things that are done, and with racing especially, we're trying to do a lot of weight savings. So we want to go and analyze that part, put in some engineering programs, and redo stress analysis on it, and then redefine how we can take weight out of the part and how we could redesign it to make it lighter. So these are just all aspects of like some things we would do for reverse engineering. A lot of things, like this is a cutting example, but we do a lot of the same stuff for, like, if I wanted to change the shift points in my motorcycle, okay, and I wanted it to click a different area, or if I want to change gearing and I need to move a shaft a little bit more, I need to move a dog a little bit more in that gearbox, that shifter drum is very important. So I might say, like, you know what, it feels a little clunky. If I change the ramp angles a little bit, it's going to be much smoother engagement for me. So, and then there's a lot of things for analysis that we use scan data for. So having that mesh model, while we might say it's not normal, like parametric CAD, how most of us think of it, that mesh is inherently usable right away for doing like CFD and things like that, and fluid flow analysis and all those other types of engineering things. It's also directly useful already in software for, and I could show a little roll cage example there, like I could scan the inside of a vehicle or whatever else and be like, hey, we need to design a roll cage for this. I can work directly off of the scan data to design all of that out and get it done. So like kind of like, what is this, a couple more random examples here, and forensics and different types of project planning for facilities, because again there's large format scanning too, where we'd scan whole buildings and stuff like that instead to figure out where equipment can go, things like that. But the whole point of using scan data is essentially time savings. And you get paid when your parts are on the market, not during the development cycle. So it's like when you ship them, when you get them in the hands of customers, you get them on their website or whatever. So condensing that time frame at the beginning of doing your design development, creating your parts and everything else, it's just money in your pocket. It's like right now I might be doing, it takes me a month to get something out the door with the ways I'm measuring things now and acquiring data. I have some digital models. I don't necessarily have archive of the parts that I've designed off of. Scan data is an immediate archive of that product and that product placement. So with a lot of aftermarket automotive especially, like I don't even have to wait for a vehicle to hit the market. Sometimes I can find something pre-market. Sometimes as soon as they hit the dealer lots, I can go out, I can acquire the data that I need. I don't have to wait for someone to create CAD data or put it online. You buy a lot of stuff probably, a lot of guys might buy stuff through SEMA Garage already and like SEMA data for designing parts around it, but you don't necessarily get everything. Like Focus came out with their ST. It's a very high performance product. Like Ford's not going to release most of the data for that car, same with like the special Mustangs and everything else like that. So you kind of are limited to what you can do on your own to come and acquire that data. So if I'm going to do a new intake for like a new for like the Focus or something like that, like I need to go out and get that data myself. Do I want to buy the car? Do I want to find a used one? Do I need to call around all my buddies? It's like, no, but like I could probably convince a dealer to give me like 15 or 20 minutes to go and acquire that data, not leaving their lot. So I don't necessarily have to keep anything on hand at that point. So I have an archive of what it is. So if I'm going to go and design an exhaust, I could probably borrow something from someone, scan it out, do it at their facility. I don't even have to like acquire the actual item. So, and then scan data is used a lot for, VR and AR too. So I kind of want to talk about that just for a second. Everybody wants 3D parts on their website. It's like one of the coolest new things. I want to be able to put something on my website. I can spin it around. I can look at it. I can zoom in and zoom out. Having those 3D textured models, like all the furniture companies are doing it now, even and stuff when you go online. But doing that with all of your parts too is a really great way to increase sales. So, and again, you could do a lot of that stuff. Like as soon as you have the first item built, as soon as you make that first frame, do whatever else, you can acquire that data before you even have it digitized for production, and you can get it up so people can see it. So you can get people excited about it, things like that. So the more complicated the things are, this is just the more time savings you're going to have using, a digital acquisition method like 3D scanning. So if you're doing simple things, maybe it's just a flange or something else like that, you need something to build up to it. It's like, okay, like is it worth like firing up the computer and taking some scanning? Well, maybe I just need 4 whole locations, maybe not. And it's just a plate, so I'm going to draw it really quick in CAD anyway. But as the complexity goes up, as fitment issues come up, as space envelopes under hood especially and things like that in vehicles, a lot of space constraints about how you can put stuff, where you can design around it. Knowing where that wiring harness is in 3D that the OEM stuck in there, or some piping. I don't necessarily want to have to measure all those things, but when I scan it, I have that instant snapshot. I can do my design work right around it, and I know all my parts are going to fit right away. So just a couple of examples of just stuff that was done. I mean, we do a lot with people do a lot with whole body scanning, but even if I needed to redesign like a different type of clutch or flywheel, and I need to know clearances. Interior panels, especially, like I want to redo a dash for my custom car and everything else. All that OEM sheet metal back there, and the air ducts, and the wiring, and everything else that I need to build around. It's really hard envelope-wise, but when I pull that scan data in, I have that envelope all there ready. And again, what makes this really useful is a bridging software. So the other thing you have to time constraint generally is getting parts in the door. So if you are outsourcing manufacturing or manufacturing in-house, one of the biggest things is how do I check those parts I get from my supplier? So I might have them send me some reports and say, hey, the parts are good or whatever else, or they go along my prints, and someone signs off on something that's good, but it's always nice to be able to double check that. Maybe I have some manufacturing done overseas. I got like my first crate in, or they sent me some sample parts. Scanning things is like the least, I would say, technical way to be able to capture that data accurately and have really anyone, with any engineering knowledge in an organization be able to qualify a part for you. So I don't necessarily need someone that's like certified metrologist that knows how to run a CMM and everything else like that. Like they can come in, easily use the same tools that they would use in their CAD environment for putting dimensions on something in a quality control program, throw the scan data in on top of the model that you guys sent to the manufacturer, and they will be able to instantly have readouts and all their measurements and all your GD&T and everything else like that. So you'll be able to qualify those sample parts as quick as possible. And again, that gets you the least amount of time to sign off on things so you can start shipping. So, and again, shipping is the goal. Like getting it out the door, you gotta ring the register, make some money. So, and it's just a little bit more about what I was saying is, the more people that you can empower to like do quality control in an organization, the better off you are and the faster you're going to get to market. So, and just a couple things on just some screenshots and some stuff for first articles. So as you can see, it's like we lay out a lot of stuff on CAD models we send to manufacturers. Color maps are hugely useful, like all these things of being able to map data on parts, pull comparison points. It gives you more than just like the general dimension stuff gives you, because you might have dimensional requirements on certain areas of parts for fitment and function, but maybe they took some leeway some other places that you wouldn't necessarily specify in measurements to check or look at and things like that. With scan data, you can't actually hide anything. You just acquire data over the whole part, and we're checking that back to a CAD model. So like if they, if they didn't grind down like a cast screw enough, or they took a little leeway on a surface, you'll be able to see that right away, and then you could always go back. It might not be a problem. It might just be something like, hey, good to note. I can always put that back in my assembly model and make sure like I don't have any clearance issues, like it's not going to rub up against anything else, it's not going to be in the way of that hose under the hood type of stuff. So all kinds of stuff on that. And then again, like, the more reliable your parts are, the better things fit when customers buy them, the happier everyone is at the end of the day. And perceived value is a huge thing. Like you have one or two people that are like, oh man, this didn't pull up the way I thought it was. That's kind of like a huge hit to anyone making parts and doing manufacturing and trying to supply stuff to the overall market. So there's a ton of perceived value in just quality. People can often charge a lot more for quality components. So, and components that people perceive that are of high quality. So I kind of wanted to I can show you a couple little things here. I got to two-hand my computer to show you a couple things what I mean, but I didn't know if you guys had any sort of questions first. If you wanted to talk about anything, or if you want to talk about kind of what they do and where some of the stuff could fit in, possibly. But anyone? No? Everybody's good? Yeah, sure.
Things like AI or machine learning helping with automated feature extraction.
Yeah, there's a lot of stuff for that. The problem is that we run into, and we do have things for pulling things out automatically, and creating those features, and creating even the extruded features or evolved features and everything else. And software does a pretty good job at it. You still need to guide it, because just because, even if the AI was really, really good right now, it might not model something the way I want it modeled. Like, it would give me a model, and I could be like, okay, I could probably edit it and do things like that. But if I was creating a part family or something like that, like I need this in 5 different sizes, like I'm going to create that model a certain way in CAD, so I can easily adjust all the things I want. And the machine learning it's not really at the stage where you can specify that intent. So it can give you a good model, and a lot of the wizards we have in our software can really help create that model. But our wizards are kind of at the feature level. So you use them to create features as you're designing through to create what you want, but you're still putting the modeling history in order and everything else like that around you. So, anything else? Anything interesting? Who all makes parts? Does it really make parts? Yeah? But, so lots of different avenues we can look at. Just gonna show you a quick thing turn my mouse on here. Almost everything requires 2 hands. So, a little example. I just wanted to show you about what are some things you can expect when you're using bridging software. Because I don't know if any of you, depending on who's used scan data and who hasn't. So So normally, if you go in your CAD software and you've ever tried to use a mesh, okay, you realize that there's not much the CAD software can do with it. It's kind of just a visual entity in the background, okay? What we do is we create all those tools where I can highlight data on it, I can extract things from it, and then I can also use it directly for modeling. So when I come in and start doing my features, okay, what I'm actually doing is, and if I just I'm just going to delete the stuff off the sketch right now so you can see it, but we're actually able to get all that data and project it out. So with the right bridging software reverse engineering, you're basically I already have the part there in 3D. I just need to create the sketches and the features and everything else to make it in the modeling, to model it in the way, the fashion that I want to model it. So we give the advent of that pink polyline. It's just reference. It's kind of like a converted entity in CAD in the background, or a background sketch that's sitting there that I didn't have to make it. But literally all I got to do is trace. So that's what I generally call it, art software is kind of like tracing for engineers. All the stuff is there. However I want to make the model or do the model, it's all there, but I already have the data. So all I have to do is go through my normal modeling workflow, and it's kind of how fast can you trace features on a part? It's sort of how fast you can reverse engineer something. So, and the more complicated it is, obviously, the more time you save. But it's sure. Oh, no, so you'd asked with the scan parts, so I don't feedback. When you scan a part, the scanner is capturing it in scale. So you don't really, I could rescale, so we do, but by default, it's dimensionally accurate to scale when it comes in. So the biggest format people use is the STL format, which was created by my company, 3D Systems. First stereolithography for 3D printing back in the day. It's kind of the bane of everyone's resistance because it's used a lot for stuff that it was never meant to do. As far as just triangle data, it is a unitless file type. Okay, so it doesn't know whether it's 1 millimeter, 1 inch, or 1 meter between points that create all the triangles. But when you're scanning, it knows all of that. So when I save that data format out, I just need to know what the units were. Essentially, that I told the scanner it was as I was capturing it. So now we can't rescale. So there's plenty of times, a lot of times for emblems and sculpture and automotive and things like that too. I might make something really cool on my scale. Lots of most artists, if they're sculpting in clay or whatever else, they might do that bust of someone, the size of their hand or whatever, put detail on it. But they're going to put it in the museum and it needs to be 4 feet tall. So we can always rescale data and then create our models that we're going to use for manufacturing or casting or whatever else. So you do that. Once everything's digital, you have all these opportunities to do all kinds of weird stuff. And then as far as like pulling other things out of like the models here, we can come in and we can do all kinds of fun stuff for creating, just like, I'm just gonna roll back here. So our software is a history-based modeler. So as I put stuff on here, I saw about it and turn it off. But lots of extraction tools. So as I come in and services, lots of opportunities to come in and get things that are quite organic and be able to fit. So I have like this organic surface right here. Okay, I can come in and grab this data, and I could fit organic things like to it as a patch panel. So lots of things open up for what you can do to come in and create, like doing that by hand. I could cut that in CAD, or I could do it the old school way if I wanted to. I can come back and cut that in CAD, set up a bunch of cross sections, draw a bunch of splines, loft it all together, make something really nice. And like if I was doing an automotive panel that was really big, like maybe I would do that. But if I'm doing a smaller part that's just cast and somebody like hand tooled something in a mold, there may be no great way to like recreate that geometry. If I wanted it to really kind of look the same as the original casting pattern. So if we're doing, like an old like water manifold on like some like 1920s car or something like that, like making that, like there was no CAD, like there was no engineers that like they did a couple sketches on paper, but most of those parts, when they finally made the molds and everything else like that, like somebody just shaped something in wood and used it to make a sand mold. So it's like so being able to capture that organic geometry, make it look the same, and just use it as it is a really powerful thing. So because again, with a history-based style modeler, I can come in and roll back and go through and just create everything that I want to create to make my CAD bodies and everything else, and just slowly build up my surface. I get my part out. From here, when I go into our CAD programs, okay, I have a full history-based model of everything that's like on here. And at that point, I can send this complete history to my CAD program of choice. So this is a super powerful thing too. We actually will go in and we will script feature per feature, sketch per sketch, relation per relation, dimension per dimension into the CAD program itself. And that'll give me a full history-based parametric model in Inventor or SolidWorks or whatever we're using, NX. So we can have that in our native CAD system like we drew it in there from scratch. There's zero difference between whether I drew it from scratch in SolidWorks or I send it over from our program after I've done a history-based model. So we have the same part, same history tree, and if I send it to someone, they would never know I didn't just do it in SolidWorks. So if you have to do like part recreation or stuff like that, this is a great way to get stuff to like end clients with like full parametric models or to manufacturers. So really powerful in that system. And then kind of the other thing I wanted to talk about is some of like quality control aspects. This is a little bit what I was talking about before. Being for like any engineer to be able to go on. I'll just do folder here. So this is the CAD model like the API I just made. Okay, any engineer in your place that does your design work and everything else, does quality control, they can come in and start laying dimensions and GD&T on stuff like right away, just like they would in CAD, and tolerance things out. If I could click in the right spots, it's bigger. So put a tolerance on. It's pulling the dimension obviously right from CAD. I'm going to add a tolerance on top of that for like what my fitment would be. Okay. Maybe I need to build a datum structure so stuff bolts together properly. So maybe I need to come in and create a couple alignment datums on a part, to get stuff to fit together properly. And then I need to make sure like things are going to interface with it. So I might want to come in and like maybe I need to put some like positions on a slot or a hole or something like that. Exact same kind of dimensioning scheme that you'd see if you were modeling something in CAD. Drop all that stuff on, and then I could do this as soon as I have my part model made. So at this point I send something out, I have it manufactured, or it gets to floor, I send it out to guys, they cam it out, they start machining stuff, And then I can have anyone come in and scan that part, and when they do that, they're just going to come in and dump their data on top of it, okay? So here's my scanned part, came from the scanner, fresh from it, it's the first part out of the shop. And then all I gotta do is tell it to like align this up however I want to fit it. And I generally go through and like fit it to like any data structure that I have with the scan data. So, and you know, I can throw a full color map on here just for fun. And I'm just gonna leave it at like 100 micron tolerance thing. So this is, you know, stuff like this is like, I drew my CAD model without draft on it, okay? And if I update here, so you'll see it will automatically update all my dimensions, all my positions, tell me whether stuff's in tolerance or not, whether it's the right size, based on the dimensions I put on. And then the color map doesn't let me hide anything. So like maybe they leaned a little too hard if they were machining this. Now this was an injection molding part, so, and I designed it without any draft on it, so someone else would draft. You know, someone else like drafted the mold and stuff like that. But maybe like if somebody was milling down this side here, and it was a deep cutter, they leaned a little too hard on one side, there's cutter deflection. This is like the similar thing that I would see. So I could tell right away that like, hey, that's not perfectly flat. You know, you leaned a little too hard on it, you gouged a little bit. You know, maybe when they were doing a face, like maybe the shell mill wasn't set up right. It wasn't perfectly indexed, or the part wasn't fixtured perfectly, and I'd see stepping in the surface if they were cutting a big face all lined up to each other. It's just one of those things with scan data, you can't really hide anything. So you just see everything there is to see about it. Whether you have it dimensioned or not, we can still check everything. We can see areas of interest that maybe we weren't even thinking about. So a lot of times with molded parts especially, you know, or castings that we have coming in, and even stuff that was just like machined out, like maybe they hogged something out a little too aggressively or whatever else in the shop, or took a little bit too big of a bite. It might not show up with like some normal like diameter measurements and things like that, but I could inherently see if like something was off. So, you know, even doing like run out on shafts and stuff like that. Normally you're going to be taking run out at a couple of locations. Depending on where you take those locations, you know, if you leave it up to the guy that wants to pass the part and say that it's good, he's going to like make sure he slides that thing along and gets the run out in the right spots, so it's perfect. With pulling in scan data, I get it all over the place. So I just see everywhere along that whole diameter for the length of the part, like exactly what's there. So it's basically like taking run out at like 72 spots, like down the part. So there's a couple of things here I can walk you. Don't want to walk you through a demo because it's just like watching people do stuff. It's kind of boring. I do it all day. But anyway, if you have any questions, you want to see some stuff, we're actually like right over there behind the tractor.
Cruising.
I can answer your questions there. And I can show you some more in-depth stuff on some of the programs. Kind of talk about like if you want to fit any of the stuff into your workflows, like how you would do that. But again, it's really about just like, getting quality parts to market or finishing projects. You may be, if you're doing project cars or something like that, it takes you a long time to make sure everything is going to fit that you're going to put in it. Like, is the engine going to fit? Like in this spot, do you have to push it back a little? Does it have to come forward a little bit? Is there going to be clearance in that transmission tunnel? Stuff like that, like all these things. You might have to fit something like 3 or 4 times to make sure stuff's going to clear now, just like doing it manually. If you digitally capture the data, we can do all that stuff digitally. We can move stuff around wherever we need it, and then pull out measurement data and/or design mounts where they need to be, right off of the frame and right off of the chassis where it needs to be. And we know when we send those parts out and we put everything together, it's going to bolt in the same location and stuff. So, and then again, it's just the amount of time it takes you to get a project through. Obviously, like no one gets paid until stuff goes out the door. So, goal number 1: get it out the door. And turn the projects over. So lots of avenues for tooling and bucks for sheet metal and things like that too. So fitting templates by hand is very hard. It's very time consuming, very skilled. So yeah, just kind of like what I wanted to go over. I don't know how much time. Normally I ramble too much, so I wanted to keep it like 30 minutes. But anybody have any other questions? All right, guys. Thanks for sitting through it.